Hey guys, welcome back. So we just finished taking the test. If you missed class for some reason, we'd be pretty easy for us to make up the test. So you just come in during your pirate time, whether that's going to be on Tuesday or if that's going to be on Friday. You'll have a full hour and a half to make up the test. So not too worried about that. It's totally fine. But let's go ahead and move on to 10-1 over randomness. So this will be the last unit that we do for this semester. We should be able to get it done, no problem, before Christmas. It's about gathering data, but all gathering data is actually based on randomness. Randomness is kind of, you would think random is unstructured because it's random, it's unpredictable, but it's actually very predictable. For instance, if we flip a coin, nobody knows. We know the possible outcomes are either a heads or a tails, just like with Harvey didn't hear Two-Face, right? We know it's either heads or it's tails. You either live or you don't live, right? The thing that we don't know is what each individual outcome is going to be. It's unpredictable. But actually, in the long run, we do kind of know what can happen, right? So let's say that you flipped a coin 5 times. We know all the possible outcomes. You could have all tails. You could have all heads. You could have 1 head out of 5, 2 or 3, right? Or 4 heads, right? But we also know that if we increase the sample size and we keep the number of trials, if we flip a coin 100 times, we know the most likely outcome is that half of them would be heads and half would be tails. But we also know we can measure the variation. What's the likelihood that we had 51 that were heads, or 52 that were heads, or 53 or 54? And that unpredictable randomness actually is kind of predictable and measurable, the amount of variation that we'd have from sampling, from sample to sample. And that really is the key and the basis for all the power that we have with statistics, to be able to claim that something is unusual or not, or if it's how unusual is that observation? Is it statistically significant? Do we have enough evidence to claim that Kristen Gilbert is, more people died on her watch than others, like we did when we started this whole thing out? So really important stuff, kind of grounding it all in randomness. We're going to apply it to gathering data, like sending out surveys and polling, or randomly assigning treatment groups and experiments so that we can prove a causal relationship, all stuff like that. That's what we'll do in this unit. But this key idea of randomness is going to follow us through the end of the year. So with that introduction, let's go ahead and move on. So the whole point about random is that their outcomes are unpredictable. So we know the possible set of outcomes, but we don't know which one's actually going to happen. The second part of randomness is usually there's some assumption that each outcome is equally as likely. Like rolling a dice, you're just as likely to roll a 1 as you are to roll a 6, right? But that's not always the case in a lot of games. For instance, in McDonald's Monopoly game, if you play, the lowest prize you could win is a $50 McDonald's gift card. So that would be the one you would expect them to make the most likely to win. Well, there are two things that you would need for that: Baltic Avenue and Mediterranean Avenue. Baltic Avenue is very common. It's only 1 in 11. So 1 out of 11 stickers on average we would expect to get Baltic Avenue. So this one is very common, but Mediterranean Avenue is very rare, and it's only 1 in 651,842 stickers that would actually appeal to reveal Mediterranean Avenue. So instead of both of these being equally as likely, they made one very common and one of them very rare, which makes sense why they would do that. And the other thing is, if you're playing this game and you don't know which ones the rare ones are, and that's pretty much how they do it, all of them are going to be common except for one of them that's going to be very rare, and that way you can't just trade them with other people and be more likely to get it or whatever. So if you're playing the game, you don't know, if you're a casual player, you don't know which ones are the rare ones or the common ones. And so you get Mediterranean Avenue and you think, oh, that must have been the common one. There's no way I'll find the Baltic Avenue. And you could be that 1 in the 651,842, and you throw yours away because you didn't know that was actually the rare one that actually had value. And how much value? Oh, $50 of value. It's not even that much. So anyway, just a way to get people to play. And if your underlying assumptions that each one of them is equally as likely, then you're going to think you have a chance, because you could easily get all of them except the very rare one and be like, oh my gosh, I'm so close to $1 million. Don't be stooped. And that goes with a lot of things. So it's good to know. All right, card games are usually based on random. So we've got 2 through 10 would be numbered cards. We got 4 face cards and 4 suits. And when you're playing the game, whatever game you're playing, the assumption is that it's been properly randomized by shuffling the deck many times. We'll talk about that on the next slide. Then no one knows what card's going to come up next from the deck, right? Unless you're playing a games based on memory, such as Go Fish, you know what cards have already been played, you know what the other person's called before. But more importantly, if you already have a pair of twos that have been played and paired off, if you reveal your pairs or your partner's pairs or whatever, then you know that if you have 1-2, there's only 1-2 remaining in the whole deck. So it might not be worth it to constantly ask them if they have that 2, because you're looking for that 1-2 remaining in the whole deck. So maybe keep quiet about that. Anyway, and ask some cards that have not been paired off in your pair or their pair. Anyway, that's how I beat 2-year-olds in the game of Go Fish. So there's my strategy. You're welcome. I actually don't like playing cards, even though I teach stats, and you probably find that surprising. You would think I'd be the one you take to Vegas, and we win big, and I get beat up in an alleyway. But that's a little too Kevin Spacey for me, and he's a weirdo, and that's true. Okay, so moving on. For some reason, I don't know. I just don't like playing card games. So how many times would you have to shuffle a deck in order to remove any pattern? So if you open up a brand new deck of cards, you notice that they're sorted in a pattern, right? You got your aces, then your twos, your threes, your fours, and then they're sorted in their suits as well. I don't know what the order is, but they're all in the same, in the same pattern over and over again. So if you do a riffle shuffle one time, and then you sort through the cards, you just look at them from their faces, you're going to still see there's going to be cards that were paired up before the shuffle, they're still paired up. Or even if they're separated, some of them are only going to be separated by 1 or 2 cards. So it truly hasn't been randomized. There's still like a residual of the pattern that started out with. So I got this little play button here. It's kind of fun. Anyway, so this is a riffle shuffle. So how many times would you do a riffle shuffle between rounds of poker or games of Go Fish before, especially Go Fish, right? Because they were all paired up. And so if you don't shuffle enough, you're likely to draw 2 pairs back to back, right? And then the game is over really fast, right? So how many times would you shuffle a deck to randomize it, to kind of start it over, fresh game, make the game last not as long? So, you're probably bored at looking at this. That's why I made the stop thing. And I know the whole time you weren't paying attention to what I was saying because you were just mesmerized by that GIF, right? So that's why I put the stop button there. Anyway, so how many times do you shuffle? So the book kind of tells us that you would actually need to shuffle at least 7 times of riffle shuffle in order to remove all residual patterns that you had in the deck before, which is pretty interesting. So anyway, 7 times. And if you were inclined and bored and at home and you had a deck, you could sort the deck whatever order you wanted to. You could put all the ones together, the aces together, all the twos. See, I'm showing my hand there. It's a pun. Oh my goodness. Anyway, and you could shuffle it 7 times and then sort through and see if you have any still matching pairs. You see if you have any cards that are still next to each other that started out next to each other or something like that. So anyway, kind of cool. All right, so to prove just how bad we are as humans at random, I want you to select one of these 4 numbers, 1 through 4. Now, before you select, don't pick your favorite number. I want you to think like robot and try to do your best to be as random as possible. So be spontaneous and spontaneously pick one of those 4 numbers. Just circle it. Go. All right, so which one did you circle? Well, what's interesting, especially when I have a full class, even when I only had a class of 5 people, the results were, there was definitely a pattern there. We did not do random very well. Even though there's still a lot of variation of what we would expect, it's really cool because psychologists show that whenever they did large samples of this, about 10% of people would choose the number 4. Okay, that's not what we would expect, right? We would expect, if we were truly able to do random, we would expect as we increase the sample size, like flipping a coin, that it would approach 50%, the empirical probability. We would expect it to be evenly distributed with 25, 25, 25. But clearly, only 10% of the people picked 4, but 75% of people picked 3. And what was amazing is in our class, when we had 5 people, 4 of them chose the number 3. What is it about the number 3 that humans are gravitated towards? I don't really know, but there is something about it. And then 10% chose 2 and only 5% chose 1. I mean, I'm a winner. I'm number 1, so I clearly chose 1, duh. But I don't know what it is. And psychologists kind of, maybe they have an answer to that. But for some reason, humans gravitate towards the number 3 or 7 or 13 or 17. So you can actually even tell if somebody's giving you, like if they're faking data, you can kind of tell if they made up the number by the numbers that they choose to use, which is kind of cool. And then there's a whole like subset of like psychology and science, which is, I don't know, kind of interesting. I should read articles on it, but hey, whatever. Another thing is that even some cultures they gravitate towards numbers, or different cultures like move away from other ones. So when I'm in China in the summer, they do not like the number 4. They're very superstitious about the number 4. I believe it's yi er san si. Yeah, so si is number 4, and it's the same word with a different tone that means death. And they, no one likes death, so they don't like the number 4. It's considered a very unlucky number. So if you're looking at elevators, no one lives on the 4th floor, because you have floor 1, 2, 3, and then 4 is actually called floor 3B. So you live on floor 3B instead of on floor 4. And so same thing with 14. They just pretend like that number doesn't exist. I'm being facetious, but you get the idea. So it's kind of cool. Different cultures, I don't know, maybe we all gravitate towards 3, but definitely in China, no one's going to pick 4, even though here is only 10%, but for different reasons in China. Okay, so if I were to select a student at random, what would that mean? 2 things. So let's say that a student says, Mr. Murphy, when you ask questions, you always pick on me. You're always asking me the question. So if I were going to back up the fact, no, I just randomly choose students, which is not possible as a human to just choose random. Like we just kind of saw that in the last one, humans suck at random. Then how would you build a case against me, right? So you'd probably say, okay, so you asked 5 questions to students today, and you asked me 3 times. So we would expect that there's 5 students. On average, you would pick on each person once or something like that, or we would need to do something in order to randomize it by maybe drawing names out, on popsicle sticks with Sharpies, so elementary school, out of a cup or something like that. So there's true element of random. We don't know which name's going to be drawn, which is kind of silly. It feels elementary, but that's actually a really good way of doing things. Should I put your names on sticks and constantly pick on you? I don't know. At some point, that's kind of mean. All right, so the first thing is that we don't know who will be chosen. So if it's actually truly random, then we don't know who's going to be chosen. We know the possible outcomes, which would be each student, but we don't know who will be chosen each time. The other thing is there's this assumption that each student is equally as likely to be chosen. So if I wrote your name on 2 popsicle sticks and everyone else's name on just 1 popsicle stick, now you have twice the probability as everyone else of being chosen. That wouldn't be necessarily fair, right? All right, so randomization is used in statistics, and I could go through and read this. I wrote this like beautiful monologue article about how randomization is used in statistics, and I could give it to you, but unfortunately you wouldn't know what a lot of it meant right now, because it's all stuff we're going to cover in the future. So if you want to read through that, or maybe at the end of the year I'm going to read it to you again, you'll be like, wow, Mr. Murphy, that was like Shakespearean for statistics. It's there, so you can read it on your assignment. And by the way, I know I don't read a lot of the notes at the beginning of the assignment and some of the little inserts there, but I wrote some of those, and like I try to make them in like relatable language, and they're kind of good. I mean, I don't have like a textbook or anything, but I think you guys will like them, and so do use those notes. I'm trying to pick the most important information for you there. So anyway, we do use randomization. It's the basis for sampling. If we don't randomly sample, then we have all sorts of biases that would come into play. If I only sample my friends or my favorite students and ask them what they think about how I'm teaching, and they all like me, I'm only going to get positive results. So I need to make sure I'm sampling everybody or randomly sampling. Either census or random sampling. Same thing with experiments. If we don't randomly assign treatment groups, if we let people choose whether or not they want to be in the exercise treatment group or the no dessert treatment group, we're going to have issues, because people who naturally tend to want to exercise more probably, or it'd be different, right? So we have to randomly assign that. We'll get into that one in a few chapters. Probability. So all of the basis of probability, which theoretical probability is based on the number of outcomes and the actual like probabilities of each outcome happening. And if they weren't equally as likely and actually randomized, then we wouldn't be able to like build models like the binomial model and the geometric model, or those distributions. And so that's very important. You'll get that again probably after Christmas. We're going to start the probability unit. We're a little bit behind, but it's okay. We'll do our best to get caught up. And then inference. So statistical inference, basically at what point is an observation so far from what we expect, if things were something, if things were fair or whatever, for us to be able to have a case to call BS and say, no, that's not likely to have occurred by chance. So for instance, I had a class of 30 students, and half of them were put to A and half for B. It was a random assignment, right? It wasn't split like we could do in elementary school. And one of my splits is 22 and 8. So 22 students were in the A section, only 8 were in the B section. So the probability of that occurring, if they were truly randomly sorted into A and B, is actually about a 1% chance, or about a 2% chance if we double it, because it was two-tailed. I might have explained that in another video. Anyway, but that is very unusual, and that actually happened to me twice. So I had two highly unusual outcomes, which means that when they made the decision, because they weren't made on truly random, but rather geographical location, for some reason there was something associated with geographical location and the types of students that I have. Honors students, yeah. So, oh my goodness, like I've got a case to call BS. Anyway, it's really exciting if you think about it. Ooh, stats is fun. This is juicy stuff. All right, so where do we get random numbers from? So if we as humans stuck at random, we can't generate random. I can't just spill off a set of random numbers. Let me try. 1, 4, 1, 5, 9, 2, 6. Okay, that was pi right there without the 3. But we can actually use the decimals of pi as random numbers. They're not truly random because we know what they are, right? But they do satisfy several tests for random. Okay, so humans aren't very good at random. See example 1, obviously. Random numbers are hard to generate. Nevertheless, several internet sites offer a limited supply of equally as likely random values, and there are tables of these random numbers in the appendix of your book, the last few pages. So here are the first row of random numbers from A123. So there you go. They're often given to us in groups of 5 just to make it easier to navigate through those numbers. We can also use our calculator to generate random integers. So if you go ahead and get out your calculator real quick, we're going to go to generate random integers from 0 to 1. So kind of like binary. And we're going to generate 5 at a time. So hit the math button, the one just below alpha. Arrow to the right for probability. Then go down to random integer. So rand int, which is the 5th option. Our lower range for values we're going to get are 0. The upper range we want 1, so numbers 0 and 1. And the number that we want to generate at a time is going to be 5. So 5 numbers of 0 or 1 randomly generated. And go. Okay, so the first one we got, okay, the first one we got was 11010, and those are randomly generated from our calculator. And I bet you got the same number. So what's the probability of that occurring? Very, very rare. So I can actually tell you, but spoilers. We'll do that later when we do probability. Okay, don't worry about it. So let's hit enter again and see what happens. 10010. I'm guessing your calculator said the exact same thing. And then again, 11000. Okay, again, the same exact thing. And 10011. So how in the world, if these are truly random integers, are we all getting the same random integers? Well, the reason is that this is what we call pseudo-random. So all of our calculators are running the exact same program or app that is generating these random numbers. So if this is the first time that you've generated random integers since a software update or a reset, okay, a RAM reset, then we're all going to get the exact same numbers. So what we can do to fix this issue is to seed the program. So the seeding is where it starts at. So we can seed, just pick a random number or insert your birthday or something like that, and we would all end up seeding and starting this chain of events at different places, which is kind of cool. But anyway, all right. So pseudo-random, this is literally the definition here, is of a number or sequence of numbers or any digital data satisfying one or more statistical tests for randomness, but it's produced by a definite mathematical procedure. So for instance, if we use pi as a random integers, that they weren't actually randomly generated. It came from like some sort of structure, just like an app that's generating random numbers. It has a structure into it, whatever that value is. And they use different ways of doing that. And there's a whole like science of random if you want to get into it, if you want to nerd out on it. But anyway, they're not actually truly random. But they satisfy all of the conditional tests that we would have for randomness. So no one knows what's going to happen next, and they're going to be like equally distributed if we do a large enough sample. Okay, so let's look at number 1, random outcomes. So for each of the following scenarios, decide if the outcome is random. So for it to be random, the main point we need to make is that no one knows what the outcomes are going to be. We know what they can be, but no one knows what's going to happen for this specific outcome. So if we flip a coin, we decide to decide who takes out the trash. I don't know, you or your little sister. Who takes out the trash? Is who takes out the trash random? So we know the outcomes, heads or tails, you or your sister or whatever, if you have her call it or whatever, but no one knows what the actual outcome of the coin flip if it's a fair coin. So that would be truly random. Friend asks you to quickly name a professional sports team. Is the team that they name going to be named at random? So the problem with this is, does your friend even know the names of all the professional sports teams? And the team that he names is more likely to be a local team, right? Or one of his favorite teams that he follows, that Google knows and tracks that he follows and constantly sends him information about because, yeah. So it's not going to actually be random. There's probably sports teams. Even if he's an NFL fan, there might be sports teams that he doesn't even know. Like, do I know all the names of the NFL teams or all the names of NBA or professional soccer? No, definitely not. I don't watch all those sports, right? So it's not going to be as equally likely because I couldn't even name all of the like European club football or soccer teams, right? I don't know all of them. Okay, so they're probably going to pick one that they prefer, which means that it's not truly random. You might actually be able to guess which team that they would name. All right, so names are selected out of a hat to decide roommates to pick in a dormitory. Is your roommate for the year random? So we know all the possible outcomes, but in this case, we don't know who you're actually going to get. So if it's done fair, if all the cards that people filled out with their names, if they're all equal size, none of them are folded differently or whatever, that might make one more likely to go to the bottom or one be higher to the top or even to be picked because it's larger or something. There's lots of things that go into that. Then yes, it would truly be random and there would be equal probabilities. We are going to get into drawing without replacement or drawing with replacement and how that changes things, but because it's still random because we still don't know what outcome is going to happen. By the way, just to prove that, I actually copied that and then reset the data, and you can see it was the same value you guys got. I should put that on the last slide. All right, many states run lotteries giving away millions of dollars, basically redistributing millions of dollars that other suckers I am so biased. All right, other people played into this game because, that's how we raise money for education. All right, so if you match a certain set of winning numbers, they use the tumbler filled with ping pong balls numbered 1 to 60 that do not replace the ball after each selection. Is this truly random? So we know the possible set of outcomes of pairs and orders, permutations, in other words, of these 6 ping pong balls numbered 1 through 60, but no one knows what set of 6 or what order of 6 are actually going to be drawn. So it is truly random because no one knows what set of 6 are actually going to be drawn. And each set of 6 are equally as likely. The only issue I might have with that is you can't have repeats because they drew it without replacement. And so if you can't have repeats, then if you guess a number like 774, then you can't have 2 7s because there's only one ping pong ball. So that would be dumb if you chose that. Many kinds of games people play rely on randomness. Cite 3 different methods commonly used to attempt to achieve randomness. Discuss the effectiveness of each. All right, so if you're playing the game Monopoly, how do we randomize Monopoly? How do we randomly figure out how many spaces you move in the game of Monopoly? Well, we roll a dice. Is that truly random? Yes, as long as it's a fair dice and it's not weighted. No one knows what outcome, and they should be equally as likely. They don't have to be equally as likely. Some games will weight some outcomes more than others to make it more rare. Because they have multiples. Like if you're playing the Wheel of Fortune, that's a good example. So in the Wheel of Fortune, how do we randomize that? Well, they make sure it has to go at least one rotation around, and then it's randomized because it's like a spinner. We don't know where it's going to stop or whatever. And they also there are certain outcomes that are more likely than others because they have several cards for the lower values, but there's only going to be one $10,000 one or something like that. Okay. Oh yeah, and then count. How many times do they have lose a turn or bankrupt or something like that? Quite often. You'll see. It'd actually be kind of fun to find the expected value of that. Maybe that's something we can do. All right, number 3. That's more of the probability unit, though. We get into game theory, which will be a fun day. Hopefully, we'll be back in person for all that stuff. All right, number 3. Another way that we can randomize. If you play any game with cards and you're shuffling the deck, that's randomizing. And whenever we do that, we draw a card. No one knows what card's going to be, what's going to come up. Okay, so get rich. Your state's lottery prize has reached $100 million. You decide to play against your better judgment. Okay. Ask Belich about it. Yeah, about playing the lottery. He'll set you straight. All right, the state selects 5 numbers on a television daily using a tumbler filled with ping pong balls, just like the last example. Number 1 through 60 replaces the ball after each selection, which means that you can have repeats in this case. Against your math teacher's financial warnings, I don't know if I added that or that was from the textbook. All right, you decide to play. You decide to pick your lucky numbers using random integers from the table below. Which numbers would you play based on the random digits? So this is what we call like a simulation. So we're going to use this random strain of digits to pick our numbers. So the way that we do this, which is not too difficult, but we're just going to pair them off into groups of 2. So the first 2 we have is going to be, okay, it's going to be 43. So that is a number between 1 and 60. So that would work. So that's going to be our first one. So our first is going to be 43. And then we have 68. But 68 is larger than 60, so we can't use that. Then we have 0 and 9, right? So that's going to be our next one, is 9. And then 87, but we can't use 87 because, again, it's larger than 60. 50, that's valid, so let's do 50. And then we have 13, that can work as well. And then 09. Now, the question here is we've already used 9, but they replaced the ball after each selection, so we're allowing repeats. So that's totally valid. We'll use 9 again. And they only wanted 5 digits, I think. Yeah, 5 numbers. So 1, 2, 3, 4, 5. So we're done. So if we use this table to randomly select our numbers, we're going to use 43, 9, 50, 13, and 9. Some people play the lottery based on their favorite. They use the same number over and over again. Like police officers use their badge number or something. It's still not a great idea. Assuming the lottery is truly random, it might make a better story if you won. Like, oh yeah, this is great. Fate. But this strategy, is it better or worse or the same as choosing? Okay, so they're exactly the same. It doesn't matter if you randomly generate numbers or if you have a set of numbers you play every single time. The randomization is actually in the numbers being selected, not how you selected your numbers. So the ping pong balls is randomized. So every set of outcomes is equally as likely as any other set of outcomes, as long as you don't mess up with the repeats and you repeated one even though they're not doing repeats. So they're all equally as likely. So it doesn't matter if you pick your random numbers or you use a random table to generate the random numbers, you still have the same very, very, very low probability of winning. And that's how they make money on you. All right, and same with casinos. Don't do it. Okay, I'm so judgmental. All right, number 10. Play it again, Sam. In exercise 8, you imagine playing the lottery by using random digits to decide what numbers to play. Is this a particularly good or bad strategy? All right. So again, it doesn't matter if you use random digits like we used or if you use your favorite or lucky numbers. They're still the same, so it doesn't matter because the randomization is on the actual selection process of the balls. So each one of them is equally as likely. 21. Beat the lottery. Many states run lotteries to raise money. Okay, a website advertises that it knows how to increase your chances of winning the lottery, which is total BS. But everything you read on the internet, totally true. They offer several systems and criticize others as foolish. Hey, my kind of people. All right, one system is called lucky numbers. People who play the lucky numbers system just pick a lucky number to play. Some of the numbers they claim to be lucky, but some may be luckier than others. Okay, this is how. Let's use a simulation to see how well the system works. So to make this situation manageable, simulate a simple lottery in which a single digit from 0 to 9 is selected. So 10 digits from 0 to 9. Is selected for the winning number. Place a single value to bet, such as 1, and keep playing it over and over and over again. So I want you to pick your numbers, whatever lucky number you want. It doesn't matter, just as long as it's from 0 to 9. And then I want you to use the random numbers to simulate it and see how you did. So I'm going to select the number 7 because most of you probably selected number 7 or 3 because you're human. Here we go. All right, so what is your lucky number? Go ahead and write that down. Doesn't matter which one you want to do. Don't do 3 or 7. Don't do 7 because that's the one I'm going to do. Okay, just do your own. All right, so what proportion of the time do you expect to win? Well, we're running a simulation of, what percent? Well, there's 10 possible outcomes, so we would expect on average in the long run, empirical probability, by the way, that 10% of the time we would win. So if we win more than 10% of the time in our simulation, then maybe our numbers are lucky. And if we win less than 10% of the time, then maybe our numbers are unlucky. Total BS. That's not how it works. Anyway, what portion of time would you expect to win? 10%. Now let's run a simulation with 100 trials. It sounds like a lot, but you're just scanning through it for one digit, so it's not that difficult. Let the numbers 100, let the 100 numbers from the table below represent 100 trials. Count how many times your number was selected. All right, so I highlighted mine. I did Control F, found all the 7s, and then changed the color. So let's count how many 7s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 out of 100, which would be 12%. So if you selected 7, that was actually better than what we expected. But in the long run, they're all going to even out. Anyway, yay, empirical probability. What proportion of time did you win? 12 out of 100, which would be 12%. Keep in mind, the simulation simply shows what might happen, not what will happen, because, again, it would be a different set of random numbers for the actual outcomes that did happen. All right, is there any reason to expect better results if you picked a luckier number? No. Oh, such as 7. We did 7, but you get the idea. All right, so in case you're curious, because of course you are, I ran all of the numbers here, just put it in Excel and then made a quick graph here. So this is a lucky number simulation for the numbers. Which one was the most lucky? So anything that is less than this 10 here is going to be the unlucky numbers. Anyone that was greater than that was the lucky numbers, at least for the simulation. We know that's BS. So the most lucky one, if you chose 9, congratulations, you had the most likely, the most probability or the most outcomes of winning than anyone else. So anyway, nothing really to learn here except random is unpredictable, but yet predictable in the long run, which is a beautiful thing. I've been talking for 31 minutes. I apologize for that, but I hope you enjoyed this. Hopefully it was somewhat entertaining and you're learning about it. If you don't want to watch the videos, you can always just read the chapter. Actually, the book is pretty good, so it's pretty awesome. I will see you guys in class, or come to class and we'll do it live. It'll be even more fun if you can.